Priya Jain, along with my co-authors Dr. B. Raghu and Dr. V. Kanna. I am presenting a topic, query optimization for cloud database. This article is mainly focusing on query optimization of database on cloud computing environment. We have taken care of implementation of such cloud databases on public as well as private cloud system. And during the research of this topic, after going through various literatures available, we found that resource allocation on private cloud and public cloud is really challenging, and we also tried to work on databases for optimization on NoSQL through various clusters. So, moving ahead, cloud computing is a buzzword from last 1 or 2 decades, and resource allocation has been quite challenging on this front. We have various public clouds available to cater the need of IT industry, right from Amazon, Microsoft and so on. There is a different implementation of a software service which includes database as a service on each of this public cloud platform with their own algorithms and mechanism. The core of Amazon Web Services is formed by the Xen based cloud computing service which is called Elastic Compute Cloud. Currently, Amazon offers two structured database services, Amazon SimpleDB and a distributed non-relational data store, and Amazon Relational Database Service, which is a fully featured relational database. Windows Azure is also known as a cloud computing platform which is provided by Microsoft, which offers similar services as that of AWS. As Amazon, Microsoft both do offer two structured database services, that is the Azure Table Service, which conceptually matches with the Amazon SimpleDB, whereas SQL Azure forms the counterpart of Amazon RDS. In this project, we have worked on MySQL and NoSQL databases on the public and private cloud with resource allocation, and we got the result for optimization of this database from both the worlds of cloud computing. Moving ahead to the literature review, let us understand what are the dynamics of cloud infrastructure. So, the cloud infrastructure is dynamic because of some characteristic features which are combined together as first, the service and access management, second, virtualization and consolidation, and finally, it is scalability and secured information infrastructure. Based on the technical characteristics, cloud technology is suitable for various applications which are having varying resource demands over a longer duration, and it needs a system that could dynamically accommodate the ever-changing seasonal demands. At present, the cloud database environment is supposed to be the best possible answer for most of the needs of programming developers. They need to store their data of their application in the backend, which can be accessed and adaptable to changes from even a single client. Now, this database as a service will benefit over a lot of traditional databases on local and server machines like MySQL, Oracle, etc. The database which are classified over the traditional RDS, that is relational data services, where we get the data an organized way of SQL query writing. For such conventional databases on cloud, we are maintaining by Amazon RDS, Google SQL, Microsoft Azure. On the other side, cloud databases like Amazon SimpleDB, Google Data Store, which are not a RDS but are based on NoSQL database concepts, which are unstandardized and does not require traditional RDBMS queries to work with such databases. There are some most popular databases in cloud computing which are mentioned as StormDB, MySQL, PostgreSQL, Google Cloud and so on. Moving ahead to the actual problem definition, we understand that the technology has entirely changed the way the traditional businesses were set up and they used to work. During this COVID pandemic, we have seen the businesses marginally shifting from offline to entirely online model, making the jurisdiction of the use of Web 2 technology. It is difficult for small enterprises to build an entire infrastructure for the business, and the obvious choice under this circumstance is moving to the available cloud resources. The cloud variable will allow to scale up or scale down depending on the business needs. It is an easy and inexpensive solution to the hosting services rather than capital expenditure towards infrastructure cost. While moving to the third party service, the user is concerned about the service availability irrespective of the failure of the provider side. Whereas, it is always a challenge for the cloud service provider to stand by the SLA, that is service level agreement norms, and maintain the efficient service. Customer will need service provisioning, and it becomes a complicated task which usually is being looked upon as an optimization problem. Handcrafting the data processing graphs that implement such services correctly, making optimal use of the resources available and the one that satisfies all the quality of service standards and other constraints becomes a daunting task. Automatic data flow optimization and execution are critical for data services to be scalable and adaptable to the cloud environment. This is an analogy of query optimization and execution in traditional databases, but with few differences. These differences are: the component services may represent arbitrary operations on the data with unknown semantics, algebraic properties, and performance characteristics, and are not restricted to come from a well-known fixed set of operators. Optimality may be subject to QoS or other constraints and may be based on multiple diverse relevant criteria. For example, the monetary cost of resources, stillness of data, etc., and not just solely on the performance. The resources available for the execution of a data processing graph are flexible and reservable on demand and are not fixed a priori. These differences make data flow optimization essentially a new challenging problem. They are also generating the need for runtime mechanisms that are not usually available. The implementation part of the project includes the following workflow. Make the connection from a server to the machine, the client machine, to connect the database for accessing the data. Store the database in the private cloud. Fetch the data from the cloud and display it on the web pages. Now this becomes the actual implementation. Now while doing so, we have to use the optimization technique to optimize the fetch data, which results in time performance of data accessing. While doing so, we plan to preserve the privacy of the data, show the result in terms of the time performance. All these steps are being done to fetch the data from a database of more than one cloud machine in a private cloud environment. Moving ahead to the results and discussions, the first graph on the screen is graph of time difference from one cloud in MySQL. The following graph is showing the time required to access the data from two MySQL databases of one server machine. When the number of rows of a database decrease, then the time difference is also decreasing. But the time required to access data is more when we are not using the optimization technique. Second graph is the graph of time difference from more than one cloud in MySQL. The graph shows the time required to access the data from two MySQL databases of one server machine. When the number of rows of the database decrease, the time difference is also decreasing, but the time required to access the data is more because we are not using optimization technique, and thus this graph shows the data from more than one server machine, so the time difference is always more related to the data access from one server machine. Moving ahead to the third graph, it is a graph of time difference from one cloud in MySQL with the use of optimization technique which is inbuilt. The following graph shows the time required to access the data from two MySQL databases of one server machine. When the number of rows of a database decrease, then the time difference is also decreasing, but the time required to access the data is less because we are using the optimization technique. Moving ahead is a graph that shows the time required to access the data from MongoDB, which is a NoSQL database of one server machine. The number of rows of a database decreases, the time required is also decreasing as per the graph shown. Finally, it is a graph drawn to depict the time difference from one cloud in MongoDB with optimization. The graph shows the time required to access the data from MongoDB database of one server machine. The number of rows of a database decreases, the time required is also decreasing as per the graph shown. The time required to fetch data from MongoDB database from one server machine is again less as compared to above because this graph is using optimization technique. So finally, we can conclude that query optimization is a multi-factor problem in the cloud environment, and the experiments that we conducted on SQL and NoSQL sample databases suggest that the time complexity can be drastically reduced with the use of optimization techniques which are actually in practice. We are proposing to conduct the similar studies to check the effects of query optimization policies in multiple environments. The authors are thankful to the cloud computing research community across the world whose experiments with the cloud databases, and they do share the results for the young researchers to follow. Thank you so much.